Giuseppe Castagna is a researcher at the French National Center for Scientific Research. In 1994, he received a PhD degree in theoretical computer science from the University of Paris, and the same year he was appointed research scientist at the computer science laboratory of the École Normale Supérieure de Paris, where, where since 2001 he directed the programming languages group. In 2006, he was appointed senior research scientist and posted at the Research Institute of the Foundations of Computer Science of the Université Paris Cité. He is the director of IRIF since 2023, after having served as deputy director for 5 years. His main research interests are contributions to the definition, design, and implementation of type systems for programming languages. So let's give him a warm welcome. Thank you.
Thanks. So thank you for inviting me to present you the it works this one, yeah. For presenting the work on Elixir. So for those who don't know Elixir, but here I guess everybody knows, is a system language of Erlang compiled by compiling to the Beam machine, the virtual machine of Erlang. And it was done a little bit more than 10 years ago by José Valim. And this work started a little bit more than 2 years ago when José wrote me because he was interested in my work on set-theoretic types and semantic set typing, and asked whether it was possible to use them to define a type system for Elixir. We started to exchange some emails, and we soon realized that there were a lot of very interesting research problems that deserved to be done in a PhD research. And so we started to jointly supervise Guillaume here, Guillaume Duboc, I for the type theory, and José, of course, for the Elixir part. And so what I will present you here is the work by Guillaume in his PhD thesis. So the plan for today is I will start to present you some basic Elixir typing, which means we just took the existing research on set-theoretic types, typing for function and polymorphism, and adapted, even though it was not easy, to Elixir. And then I will present you the three main problems we tackled here for Elixir. The three problems were how to do type inference for pattern and guards, how to type maps, and how to add gradual typing to Elixir. At the end, I will finish presenting you the progress of the current progress of the project, and if I have some time, the future work. Okay, so let's start with the basic one. So type checking 101 is well, if you in Elixir define a function gate that checks whether its argument is of type integer, and you apply it to the function not, and you know Elixir program, you know that this is a type error because not is defined just for Boolean, not for integers. And so the very basic things you expect a type system to do is to have such kind of error. Okay. But if you write now as you should, that is, you use the minus sign here, okay, and now you can say, well, check whether this function is type integer to integer, and we use this dollar sign to declare the type of the function that follows, okay. And the system say, oh, okay, that's if you give it an integer, you obtain integer, so it is well typed. And so you can use this function for other functions. For example, for a function subtract, that takes two integer and returns an integer. And indeed, here you have negate that is applied to b, which is an integer, so it returns an integer, and then plus is happy and can compute an integer, and this is well typed. Okay. So far so good, you are really at the very basic level, but what if we modify the implementation of negate? For example, let's put both clauses that we define. So we define negate now so that if it is an integer, it does the opposite, and if it is a Boolean, the argument it does not. Then the type here, well, now it is a function that can take either an integer or a Boolean and returns either an integer or a Boolean. And so we define this type. It is a function that takes an integer or a Boolean and returns an integer or a Boolean, where this OR is a union type. Okay. So far so good, but now our subtract function doesn't work. Why? Because, well, here you have negate b, it is applied to an integer, it's okay because negate works with integer Boolean, but the result is either an integer or a Boolean, and plus doesn't know how to work with the Boolean, so the error says, oh, I was expecting an integer here, but the second argument, the argument can be also a Boolean, so it doesn't work. And the second argument of plus can be a Boolean. The problem here is that the type is not enough precise. You have to use a more precise type, what is called a subtype, okay, and give this type to this function. Say that negate is a function that when you apply it to an integer, it returns an integer, and when you apply it to a Boolean, it returns a Boolean. And this and here is an intersection type. Okay, and now subtract works because the occurrence here of negate is applied to an integer, so we know that in that case it is an integer that is returned, so it type checks as before. Okay, so this I show you the usage of union intersections. The other things that we have are singleton types and negation type. And to show you their usage, consider this negation function that when applied to false or nil returns true, and in all the other cases return false. So the type of this function is a function that when you apply it to false or nil gives you true. And you see these false, nil, true are singleton types, that is types that type just one value, which is the value of the same name. Okay. And when you apply it to something that is neither false nor nil, then it returns false. And this is a negation type, not is for negation, and it types all the values that are not in this type, the type it negates. The next thing that we added is polymorphism. Okay, classical example of polymorphism is the map function. I don't comment the code of the map function, but I comment our type, which says that map function is a function that takes a list of a function from A to B, and it returns a list of B, where A and B are type variables. We have this notation for type variables, and you see we also have bounds for the type variables. Here, term is the top type of the Elixir type system, and therefore it says that A and B can be any type. Okay, and we use local type inference for polymorphic functions, in the sense that you don't have to specify how to instantiate the A and the B when you apply the map function. The system does it for you. So, for example, here, if you apply map to a list that contains just one element, which is a pair of an integer and true, and the functions that takes a pair, checks whether the first argument is integer and gives the first argument, then you know that what you obtain is a list of integers, and this is what the type system does. And of course, you can combine all these things together. For example, you can combine intersection and polymorphism. To give you an example, consider the logical OR as it would be done in JavaScript-ish way. That is, in logical OR, you check whether the first argument is falsy. Well, here just false or nil. Okay, in JavaScript you have 8 falsy values. If the first argument is falsy, then you return the second argument. Otherwise, you return the first argument. Okay, and the type here is the following one. This is a function that if the first argument is false or nil, then it returns the second argument. Okay. And if the first argument is of type B, which is neither false nor nil, you see here the bound, then whatever you can pass whatever you want as a second argument, it always returns the first argument. And here you see a combination of intersections, bounded polymorphism. Okay. Okay, this was the thing that there is existing theory. We adapted it to Elixir, and so far so good. Actually, they allowed us to solve things that were not used before. This type were not used for before, like for example, typing protocols. Doing parametric protocols, etc. I have no time to present it here. Let's switch to the things that new here. So, first of all, the inference, type inference for pattern and guards. Okay. So, first observation. If you do type analysis for pattern and guards, then you solve two problems. One is how to type case expression, and the other how to type a function with multiple clauses, because as you probably know, these two functions are exactly compiled in the same way. Okay, so I will speak of them without making any distinction. Okay, so then the things that you want to check when you do cases is exhaustivity and pattern matching, essentially. So consider this type. This is the type of records that have exactly two fields. Okay, a first field is output, and if the first field is output and has value OK, then the second field is socket of type socket. If the first field is error, then the second field is a field message, and it is either an atom timeout or a pair delay integer. Okay, and you see again, I use here the union type for this. So imagine now that I define a function handle whose input is result, okay, and this function does, if r.output is okay, then message receive. If it is not okay, then I know that the second field is message, so I do r.message. If it is timeout, I do something. And of course, it is well typed, but there is a warning, say, hey, here there is a missing case, because you can also have the case in which you have the output error and the message, which is a pair, not just timeout. Okay? For redundancy, well, now we write the handle in the right way. We check if our output is okay, we do something. If our output is error, we do something. And then we check something else, but there is no other cases. So the type system will say, the last branch is never used, you cannot ever select it. Another thing that it is interesting when you do type analysis for for guards and patterns is what is called narrowing. An example here, so let's take now the handle and do it in a more complicated way. So again, we say that handle takes a result as argument, and then we use this underscore to say to the system, hey, compute me the return type, please. Okay, so if the input output is okay, then I know that I am in this case. So the second is a socket, so I return accepted, and I can select socket. Okay, if otherwise, I know that the output is error, and I check whether r.message, because here there must be message, is an atom. If it is an atom, is timeout, then I return timeout as a result. Okay, and otherwise I know that it is a pair, so I select the second component of the r.message. And the system tells me, well, what you expect. It gives you these things except a socket. Here it gives me timeout, and here it gives me a retry at an integer. Okay, but actually, so the important thing is that to do this deduction here, the system must narrow the type of R here. For example, here to see that this r.socket is well typed. It must deduce that R has not all this type, but just the first element of the union, okay? And this is called narrowing, because you take into account the result of pattern matching to specialize, to refine the type of the variables inside. Actually, our system can do more. Actually, can deduce this precise type that says, if you give me something of this type, then you obtain this. If you give me something of this type, you obtain this, etc. How to do that? Well, very simply, you just remove the type annotation, and our system takes all these guards as very sophisticated type annotations for the function, and it deduces that he has to infer this intersection type, which is not so easy. Okay, so that's really complicated, so let me show you a little bit of formalization. Sorry, I'm a theoretician. So the formalization, what we did is that we define a calculus, okay? It's pretty standard one. The only things that I want you to notice is that here we have union, intersection, and negation, the types, also type variables, of course. For functions, we have multipolarity for functions, and of course we have the case with pattern and guards. And the other things is that we consider pretty sophisticated, a pretty complete set of guards in which you have Boolean combination, checking of types, relations that are on selectors that are not so trivial, okay? You can select very peculiar things. And the next thing we have to do is to define the subtype relation. And to do that, what we do is that we associate each type to the set of values that it types. So Boolean is interpreted as the set true, false. Integer is interpreted as the set 0, 1, 2, etc. The union is the union of values, the intersection of values, and the negation are all the values that have not the type. And then you define subtyping as set containment, okay? The other things is that you want to, for patterns, to associate also a type. For pattern, there is a set you want to give, is the set of all values that match the pattern. But unfortunately, this is not always a type. So what you do is that you approximate it by a slightly larger and slightly smaller type. So we define the serially accepted type of pattern guards as the largest type that contains only values that match the pattern, and the possible accepted type is the smallest type that contains all the values that match the pattern. Let me show it on an example. Consider this guard, okay, this pattern guard, and this is a pattern guard that matches all the maps of size 2 or every list, okay, and there isn't a type for maps of size 2, okay? So we have to approximate it. And therefore, we approximate it by the possibly accepted type. The possibly accepted type is a map union list, because this pattern guard can only accept either maps or list, while the surely accepted type is list, because all the lists are captured by this pattern guard, okay? Formally, the properties is that if V is in the surely accepted type, then V matches the pattern guard, while if V matches the pattern guard, then V is in the possible accepted type. Which means that these two types, remember these are types, are the smallest type, which is the smallest type or the largest type, which are over approximation and under approximation of the set of all values that match the pattern guards. Once we have done this, then we can use it to type cases, okay? So consider the case expression in which E is type T0. And to type this expression, we have to find the type of the values that can be processed by the branch EI, okay? So these values is the type TI, defined like that. Let me explain it in words, okay? So in words, the expression EI will process all the value, may process all the value that are in the type TI, and these values must be, of course, generated by the matched expression, so they must be in T0. Of course, they must not be captured by a previous branch, so they must not be in the surely accepted type of the previous branch. And of course, they must be captured by the current branch. So they must be in the possible accepted type of the pattern guard of the current branch. Once we have then done that, then we use this TI in a rule that I will not explain for cases. Just I want you to observe that here we use this TI just to deduce the type of the capture variables of the pattern. And we have here a condition that says that all the values that can be generated by E must be in the union of the possible accepted type, which is the exhaustivity condition of our system. And finally, here we have a small condition that says that the result is computed only for the branch in which the TI is not empty, which means that the branch can be selected, and this is used for computing redundancy. Okay? If you think that this rule is complicated, the actual rule is much worse, okay? So no, I won't comment it. I just want to show you this part here. This is the guard analysis, okay? This is the guard analysis. This is the premises of this rule. And look at there. What it does, it takes the list of all the pattern guards and produce a list of pairs. And these pairs, the first one is a type and the second is a Boolean. So let me again show it on our example. Consider again this pattern guard, which I repeat captures all the map of size 2 and all the lists. And now you apply this judgment here, and it returns this list. The list map false and list true. And now you see that this Boolean tells you whether the type associated to it is precise or not, because this pattern guard doesn't capture all the maps. It captures just the maps of size 2. So it is not precise. You have false. While list is precise because this pattern captures all the lists. And now it is very easy to compute the two types, because the surely accepted type is exactly the union of the types which have the true flag, while the possibly accepted type is the union of all the types in the list, okay? And this kind of listings allows us to have a very precise typing like that. Look at this function here. This function is a function that checks whether the first is Boolean, or first argument is Boolean, or the second argument is an integer and returns them swapped. And our system, thanks to this kind of analysis, knows that it has to compute an intersection type. One case for the second is an integer and the first can be anything, and the one for the first is a Boolean and the second can be anything. And you really need this kind of precision to deduce this kind of types. Okay, next, maps. Maps I will be very fast. Because there will be a talk at ICFP on that. So I will just show you an example. In Elixir, our syntax for maps is the following one, okay? So this is the type of maps in which there must be a field foo of type atom. There is a optional field bar of type atom, which means if there is a field for the key bar, then it must be associated to an atom, and there is an optional field that say and any other atom which is not bar or foo must be mapped to an integer, which means if there is another atom and it is different from foo and bar, then the field must give you an integer. Okay, so in practice, what does it do? If you do m.foo, well, the system tells you, oh, okay, you obtain here an atom, easy. But if you do m.bar, then you have a type error. Why? Because m.bar, if bar is not present, is an error at runtime. Okay, so you want to capture it statically. Okay, but if you want to do these things, then you have to use this notation, which differently from the first one, doesn't give you an error when bar is not present, but it gives you nil. Okay, and so the type system tells you, well, if bar is present, you have an atom. If it is absent, you will have nil. If you now give a key that is neither foo or bar, then it is the third things here that applies, and therefore it deduces that what you obtain is integer, or if a field the other is absent, nil. The other thing interesting of this notation is that here you can put an expression, not just a nominal key. So let's do it and use it here m.foo. Okay, m.foo, the system says, oh, m.foo, it is an atom, so here I have an atom, so all the three cases apply, so either I obtain an atom, or an integer, because in the last one, or nil, because it is absent. Okay, and of course, if you try to use an expression that cannot produce any atom, then the system tells you, oh, here you will always obtain nil, and you will have a warning, say, that, well, if you try to select something that always gives you nil, maybe it's not completely correct. Okay, and then, as I said, there is a talk on how all these things are done at ICFP on Wednesday. Last things, gradual typing. Gradual typing, what is gradual typing? Well, it's a technique to blend statically typed and dynamically typed code, which is fundamental here because you don't want to migrate all the existing code to the typed code at once. You want to do it gradually, and to do that, what you do is that you introduce a dynamic type, which is a type that just say, well, at runtime it may turn at any type you need. So if you have dynamic, you can imagine that it can become any time you want. You need to type check. So this, of course, offers more relaxed safety guarantees, because if your system tells you that an expression is type dynamic, well, it doesn't say anything apart that it is well typed. It can be anything, okay? It can be any type. But if the type system tells you, oh, this expression type integer, then you know that if you obtain a result, it will be an integer. Okay, this kind of guarantees are the same guarantees that you obtain in the approach that usually is called sound gradual typing, but with a huge difference. Is that when you do sound gradual typing, usually the compiler inserts typecasts at the compilation to check effectively this soundness. Here, José was clear. The types must not influence the semantics. You don't change the semantics of Elixir, okay? So the problem is how to obtain the same kind of level guarantees without inserting typecast. Well, we have the chance that Erlang, Elixir are already do, the virtual machine does a lot of checks at runtime, but also there are assertive programs in which the programmer puts checks at runtimes. Every time you write a guard in an Elixir or Erlang, you are doing a runtime type check. So the idea is how to do gradual typing using as much as possible the check that is done by the virtual machine and those inserted by the programmer without changing the compilation. So what we came out is this notion of strong functions. Okay, so let me explain it as an example, by an example. So consider the identity function, and you decide that you say that this identity function is type integer to integer. Okay. Now, if you apply to an argument of type dynamic, the type system tells you, well, what you obtain is dynamic. Okay, you give me garbage, I give you garbage. But probably a Erlang and Elixir programmer wouldn't write this function like that. If they write the identity function, they would write it like that. That is, it is the identity function, but I check whether the argument is an integer. And now the function is pretty different because you are sure that whenever it returns a value, it will be an integer. Or it fails, okay, or it diverges. Well, here it doesn't diverge, but it always returns an integer. So you can say that id strong of dynamic returns an integer, okay? So we have this function with the strong types that give you the guarantee that whenever they give you an output, the output is in the codomain because the programmer inserted the right check, the right guards to ensure that. Okay, so we use these things, but there is a price to pay. Okay, because consider again negate. Well, you see, negate is a strong function. You know that you always obtain either an integer or a boolean. So you can say, oh, okay, strong function, I obtain integer or boolean. But now, if you have subtract, you don't do any check. So if b is dynamic, negate of b is dynamic, so I obtain integer or boolean. Oh, it doesn't work. Same error as before. Okay, because the sum expects an integer, and here you give me an integer or boolean. But you use dynamic at the very beginning, so you want to propagate the flexibility of dynamic. So what you do, well, our solution was to, so you obtain an error. Our solution was to add these things. Say, what you obtain is a integer or boolean and something that is dynamic at the very beginning. And now, when you try to type these things, you say, haha, here, negate b gives me an integer or boolean and a dynamic, so it is dynamic. It can become everything you want, so it can become an integer, and then it is well typed. So the result is integer. Well, actually, integer and dynamic, because we still propagate the dynamic. Okay, so these are our two small solutions for doing gradual typing without touching the compilation. Okay, and of course, if you try to use negate in a place in which there cannot be either an integer or a boolean, then you still obtain a static error. So if you try to use negate in a concatenation, then it tells you, no, at least must be an integer or a boolean. Maybe one of the two thanks to the negate, but it must be one of these two, okay? Perfect. So that was my presentation for what we did. So our project, the progress, at the very beginning we had some milestone to formalize a rather complete type system for Elixir, define the syntax of types, implement the prototype, present our design choice, publish our approach, and integrate the system with the Elixir compiler. And we currently are at the phase 5 and 6. It makes 3 months that Guillaume, the PhD student, is implementing in Elixir. We have a prototype, not in Elixir, but implementing in Elixir these things. And for the presenting our choice and publish our approach, well, everything I told you here, there is a paper that is also on the web page of the workshop. This one, which will appear next year. You have also the preprint. And actually, we have the final version for September 22nd. So if you have comments, you can send us before that. That will be very welcome. And for the prototype, there is an online prototype where you can test nearly all the things that I show you, not the maps as I show you. And okay, gradual type is not very well done, but all the rest works pretty well. I say it is highly experimental, and I mean highly experimental. Okay, and let me finish for the future work. I still have a little bit of time. So future work, these are in order of priorities the things that we want to do. So we want to type first class modules. We want to do row polymorphism for map. We want to put some flavor of type reconstruction and occurrence typing. We want to type process and communication, and we want to add behavioral types like mailbox types, session types that we will see. I'm very eager to see it here in ICFP. Okay, so actually this is my list. José's list is this one. Okay, so the first 3 things are the things that if we succeed, it's very likely you will see it in a future release of Elixir. So I have a slide for each one. let me speak of behaviors. So, when you have an Elixir module, the visible part of the module are four things: the name of the module, then you have a bunch of types, then you have a bunch of declaration of callback functions, that is the functions that the implementer must implement to have an implementation of this module, and then you have the function provided by the module. So this is like deferred methods, and these are like frozen methods that you cannot modify. Okay. And what I want to make notice here is that, well, this is a standard module, GenServer module. And here in start, the first argument is of type module. So the start takes a module as an argument. Actually, it doesn't take any module. It must take a GenServer module. But there is no way to say that it must be a GenServer module. So what we want to do is to replace here this module here by a type that describes the visible part of the expected module. And the visible part, well, there is different degrees of visibility, especially for the types, because the types like optional result that gives you the option of every server and the result that you expect from every server, that they must be transparent, they must be visible to everybody. While the state used by the server, you must not be able to manipulate it. It must be opaque. So only the function of the server can use them. And finally, the types like request and reply, that are the type of the request and the type of the replies of the server you want to implement, and that are used here for the callbacks function and also in some other types. Then these must be parameters of your module. Like you define a stack module, it's parametric in the type of its element, but then when you have a stack of integers, you want to be sure that you will push only integers, and pop you will obtain an integer. Okay, so the idea is to have a types like that, in which GenServer now has two type parameter, request and reply, that are used in the other types and in the type of the callbacks. The type optional result are completely defined. They are transparent, while state is completely opaque. It's just a name, so you cannot do anything like that. And the important part here is that now start takes a GenServer module of exactly the same type of what you are defining. Okay. Row variables. Do I still have the time? Yes. You want 5 more minutes? I need 3 minutes more. So row variables. The classical example of row variables is delete. You have a function that takes a map and deletes the full field of this map. Currently, the type we can give it to it is this one. It says it's a function that takes a map and returns another map. This means open in Elixir, in which the full field is undefined. Why? Because it's an optional field foo of type none, which means if foo is present, then it must be associated to a value of type known. Known is the empty type. There is no such a value, so it must be undefined. Okay? And that's completely useless. Why? Because if you apply this delete foo to a record with the foo field, the bar field of type boolean, and now you try to select bar of the result in the result, well, you have a type error, because it says, this is the result type, there is no bar there, so wrong. Okay? The solution is well known, very used, especially in the ML community, is to use row variables. It dates of the 19th, to use row variables. This is to say, what you get here is a record with some fields A. Is a row variable for fields, and then what you obtain is also a record with fields A, but where foo is undefined. And now, what the system does is unifies A with the type of the argument, and it deduces that there is a bar in there and gives you Boolean as a result. Type reconstruction. Okay, so very fastly here, we have to do some type reconstruction. I already did some kind of type reconstruction. For example, when I show you this example of map, you see this function has no type annotation. So I in some way reconstructed the type of this. Well, that's not really true, okay, because there is here a guard that tells me that the first one is an integer, okay? So, but if I didn't put this guard, what should I do? Do ML reconstruction? It is expensive. It's very expensive in the presence of set-theoretic types. Like there, this is very well known how to do this, but when you don't have set-theoretic types, when you have union intersection negation, there's a problem. So there is a trade-off between what we will do and the time it takes. And finally, my last example is the occurrence typing. So consider the filter function. The filter function is a function that takes a predicate on A, a list of A, and returns the list of all A that satisfy the predicate. But actually, this is not what the types say. Okay, the type says, oh, it takes a list of A and returns a list of A, and that's, we can do it, okay? But what we would like to do, and we are not yet able to do it, is to give this type, which is a function that takes, a function that gives true for the element of type A, gives false for the element of type B. It takes a list of A and returns a list of A that are not B, okay? And the problem here is we need very powerful occurrence typing. We need to be able to deduce that by checking the result of this application, we must be able to deduce how to specialize the type of fun and H in there. The theory exists. We submitted it to NextPopo, so don't know why it is in limbo. It exists, but it is very, very expensive, computationally expensive. So we don't know, again, how much shall we put of this? Which are the trade-offs in terms of complexity? This was my last slide of presentation. So I concluded with recalling the milestone, the paper, the prototype, and a little advertising. As you see, we have a lot of future work, but we lack both people and money to do that. So we are looking for student postdoc to develop future work and sponsor for this work. If you are in one of these two categories and you're interested, please contact me. And thank you very much.
Thank you very much for such an interesting talk. Maybe while the
switch it on.
Maybe the other speaker can start setting up, and we can take maybe one question. Two, then.
So how do I understand dynamic? Dynamic is not any.
No.
It's basically any or crash, or what does it mean?
Dynamic means dynamic can be anything, okay?
Anything can happen.
Yeah, but for example, the subtyping relation is completely different, okay? Any dynamic is not a supertype of everything. Dynamic negation dynamic is exactly the same type. While for any, one is top type, the other empty type. So it's really a different type. It's a special one that the only thing is that it can become anything you want at anything you need at runtime.